that dE, right, our dE was what it was, dQ plus dW, right? This is the work, and we explained that the work is basically dW is our generalized forces multiplied by generalized coordinates. Okay. And we explained what exactly those forces are and what are the coordinates, etc., etc., etc. Okay. So this is, for us, this is the first law of thermodynamics. Okay. Now we are going towards the second law of thermodynamics, because this is nice explaining something about the energy, but the second law of thermodynamics is going a little bit further, and it starts with, well, first of all, what we are talking about. All right, so there are energies, but energies of what? Energies of matter, energy of the system. But when we measure the energy, our claims about, okay, so the change of the energy, the applied work on the system, the heat, we always measure the energy at some specific states. And those states we call equilibrium states. Equilibrium states. Okay. We already mentioned those states yesterday. Right? So basically those are the states that the system that are not modified as a function of time. They are stable. There are no currents present in equilibrium states. And most of the dead matter around us, we can assume that they are in equilibrium. Right? This is very crucial. There shouldn't be any currents in equilibrium state. So the moment that you see any kind of a current, even macroscopical current, you know that the system is not in equilibrium. So for us, stability basically means equilibrium. Although there can be some other kinds of stability, but for us, stability and independence of time, this is the equilibrium state. So when we are talking about the modification of energies, the work, etc., etc., we are taking the system from one equilibrium state and we are somehow pushing it towards another equilibrium state. So all the transitions that appear and will appear in this class are transitions between different equilibrium states of matter. Everything is in equilibrium, we can do something about it, but eventually we take the system from state A, which is an equilibrium state, and we somehow, by some process, move it to state B that also is going to be an equilibrium state. Whatever we are doing in between, well, we can use different kind of processes. So B is also equilibrium. In between, we usually will do something. And as we saw in the class on thermodynamics, usually you apply some quasi-static process, etc., reversible, etc., etc. We'll see in a second. But thermodynamics deals with equilibrium states, at least in this lecture. Okay, so we know something about energies. When we change energies, we are going from one state to another. Those states are equilibrium states. And the second law of thermodynamics is the law that is used to define what is an equilibrium state. Okay, so I'm telling you, right, there is an equilibrium state, this is a stable state, etc., etc., etc. But how we define it mathematically, rigorously. Okay? So this is the second law of thermodynamics. And the second law of thermodynamics says the following. There is a function there exists a function of the energy of the system and different coordinates, generalized coordinates of the system we call it S. It's a function of E and X. The name of this function is entropy. Okay. So up to now, I haven't said anything to you. I just said, well, I can create any function, and it's going to be a function of energy, and it's going to be a function of the different coordinates. But the statement of the second law of thermodynamics is as follows. If a state B can be reached adiabatically from state A, then SB is larger than SA. All of this statement, this is for us the second law of thermodynamics. Now, quite mathematical and probably different from what you have seen in thermo class. But the only point that's missing here, in a sense that I haven't told you anything about it, is this: what does this adiabatically means, right? So we talked about systems and we talked about generalized forces, and we almost haven't talked about what is this heat over here, right? So I told you, yeah, I can light up a fire, I can boil water, there is going to be vapor, the vapor is going to produce some work, so the heat is a kind of an energy. Okay. How do we control it? So we can turn out the fire, or we can, and this is the idea of thermodynamics, we can create constraints or boundary conditions such that the system or the heat is not escaping from the system or entering the system. Okay? So in usual work, we can add more pressure, less pressure. For heat, usually we apply adiabatic conditions by saying if the boundary conditions are adiabatic, adiabatic means no heat exchange. Okay. So you take a system, you leave it on its own, right? So, and you do not do anything to the system, and you definitely don't let the heat escape the system or get inside the system. And if the entropy, or if the system on its own will move from one state to another, this means that this entropy of the second state is larger than the entropy of the first state. Okay. Moreover, just a second, there is another condition for this S, E of x. So S, E, and x is a monotonically growing function of E. Okay. The larger is E, the larger is your S. Yes, you had a question.
I understand.
All right. Okay. So this is the second law of thermodynamics. And we are going to use this entropy to define what is a state, how the state, why the state, and what happens in equilibrium states. But it's always going to be something about equilibrium states that we deal with. Great. So we have some mathematics to work on. So we have some conditions of a function. We know something about the energy. Okay? So this is the first law of thermodynamics, conservation. The second law of thermodynamics, yeah, there is a function. It's a growing function of energy. And there is some sort of a maximal principle, right? So if you think about it, there is a maximal principle that's stated over here. You have two states. Which state is going to be occupied? The state with the larger entropy, right? Because what is said over here? What is said over here, if you take a system, and because of this adiabatic constraints, the system on its own will evolve to another state. Equilibrium is when the system stops evolving, right? So it starts at some state and it moves to state B and C and D, and then it's not evolving to any other state. It's going to be constant as a function of time. What will happen to the entropy? You started with some specific entropy at state A. Then the system evolves to state B. There is a growth of energy. Of entropy. The system evolved into state C. There is an additional growth of entropy, etc., etc. At some point, the entropy stopped evolving. What happened? It reached its maximum value. Okay? So the statement of the second law is there is a function, call it entropy. Don't really understand what it is, but this is a function. It's a growing function of energy. And in equilibrium, it's going to get its maximum value. Okay. So this is important. So we have something about the energy, the control of the energy, and we have some principle. Usually in physics, it's enough to already to start a big theory. Right? So if you remember analytical mechanics, there is a starting point. What is the starting point?
Lagrangian.
Lagrangian. But before Lagrangian, right? Before Lagrangian, you have Newton equations. In Newton equations, those are the points when, at least at the first year of undergrad studies, this is the starting point of everything. And the second year, you suddenly see about, no, you don't have to start from these equations. You have to start, you can start from some maximal principle. There is an action. What exactly this action? Well, there is a formula, okay? But it has to have some minimal or maximal property, and then all the equations pop out. The same idea applies to statistical physics and thermodynamics. You have a function, let's call it entropy. I don't really understand what it is yet, okay? But it has some maximal or minimal property, which is variational property, and we're going to explore it and utilize it in order to get everything that you need to know about thermodynamics. Yes? Good.
אם אנטרופיה תמיד גדלה, אז למה זה לא נראה ככה לדוגמה שאני משנה מצב צבירה במוצק ואז...
Okay, so
מספר האפשרויות מצטמצם.
Alright, so the question is, if the entropy is always growing, okay, so why sometimes that I modify my phase of matter, the entropy is dropping down or dropping up? We will see the constraints. So you see there is something about the energy. When you heat up stuff, maybe the entropy will grow or maybe it will decrease, but it's still going to be this function. So if you account for all the entropy of all the system, it has to satisfy this condition. So sometimes you see on the part of the system, you look on big, like for example, the entropy of something can go down. But the entropy, the total entropy of this, in this class, has to go up or stay constant if it's in maximal value. So it depends if your system is isolated and under adiabatic conditions, then this applies. If you're looking on some system that is a part of a big world and there is exchange of heat and exchange of everything else, yeah, sure, your entropy can get down. You have a messy room, right? So the mess is your entropy. Okay, so if you leave it alone, the mess will only grow up and up and up. If you don't let your mother come into your room and settle things up, all right? So the mess will exponentially grow up. But from time to time, somebody comes in, settles everything, and it looks like nice and neat. The entropy goes down. Why? You applied external energy. My mother, your mother, whatever. Okay? No. There is a work that was performed in the system. Work can lower down the entropy. Okay? There was an external work that was applied. Okay? Other questions? Yes?
This is similar to, I think, the action principle. Where
exactly.
Yes.
Yeah.
So, if I think maybe like a three-body problem, I don't know exactly how the system will evolve, but I do know that it will satisfy that the entropy will always increase. So eventually it will reach the same sort of state or...
Get to the question.
The question is, if I have a three-body problem,
Yes.
and I evolve it like two systems of three-body problems, and each evolves through time, they both will chaotically differ, but they will both reach the same equilibrium state after time.
No, it's a small system. You cannot. There is no equilibrium. The idea is not applicable to small systems. You remember before yesterday we talked about huge systems and specifically the extensivity of energy. It's a critical condition. You have to assume that your energy is extensive. Three-body problem is not applicable. Okay? Yes.
I can think of a system, maybe an isolate system, and if I will apply, let's say, an external magnetic field, if the material inside is ferromagnet, I decrease the number of possibilities.
Well, you do it. You perform work on the system, right? The moment you do something to the system, it's not applicable anymore, right?
Okay.
It's not that the entropy cannot get down. It's saying if you take system, you do not do anything with it, right? You rattle it like this, all right? It got into a specific state, and then you leave it alone. As a function of time, the entropy will go up, and eventually it will reach a maximal level that will define the equilibrium state. That's it. If you're applying stuff on it, if you're doing something on it, if you're continuously rattling it, it won't go to an equilibrium. And if it won't go to the equilibrium, the entropy won't go to its maximal value. Or vice versa. Okay? So both ways. You have to leave the system alone. You cannot touch it. You cannot do anything with it. Only then this principle is applicable. There is a general question about our universe. The finiteness of entropy and what goes with entropy in our universe. It's also related to very deep questions about irreversibility of time, etc., etc. Not the place, not the time, and this lecture. Maybe later. Okay, so let's do something constructive. Constructive is mathematical equations and etc. Because philosophy won't get us too far. Okay, so what I want to do is to use a little bit properties and define additional quantities. Specifically, I want to define a very temperature. I want to define temperature. Okay? Because entropy I cannot understand. Heat I don't really know what it is. But temperature I have a feeling about it, right? I can have a thermometer and the thermometer will show that my temperature is 36.6 degrees Celsius. Okay, so we are familiar with temperature. It hasn't appeared yet at the lectures, so I want to define what temperature is and where it's coming from. Okay, so and we're going to use some ideas about entropy and etc., etc., etc. Okay, so we start with our entropy, which is a function of energy and x, and we want to say the following thing. So everything about thermodynamics is an assumption that everything can be defined as some generalized function which is continuous. Sometimes it can be discontinuous, but everything about thermodynamical theory from the 19th century, that everything is a big function of a lot of parameters, a lot of variables, and we will going to use, and we always assume that the function is differentiable once, twice, whatever. Okay? So we start with the entropy. Okay? And we want to play a little game with it. So let's take a differential of the entropy. There are two general variables, so we can say that it's ds to dE, while setting x constant. This sign over here, outside of a parenthesis, says what variable I kept constant when taking this derivative. So d is dE plus ds to dx, keeping energy constant, dx. Now, when I write down this ds to dx of E, I'm basically saying this is multiplied by dx. I basically say that this is ds to dx1 plus ds dx2, dx2 plus etc., etc., etc. I have many variables. Alright, so this is the differential of the entropy. We already seeing what is the differential of the energy, right? So the differential of the energy is dq plus f dot dx. Now, if I'm saying the following thing, if I'm starting from one specific state and I'm moving to another specific state and I'm using a diabatic process in between. Moreover, the process is also reversible. So what means the reversible process? So if I'm starting at A and I can transform to B. If I reverse everything, I will go from B to A. So the moment that I have reversible processes, it doesn't really matter if I'm at A because I can go from A to B, or I am at B and I go from B to A. Okay, so the moment that I have reversible process, means that ds equals 0. Okay? So this guy is going to be 0. Adiabatic means dq equals 0. Okay. So I'm starting at some state. I am using a reversible process to reach another state. On the way, there are some modifications of the energy. There are some modifications of the entropy. But I know that ds has to be 0 and dq has to be 0. Okay. If those two guys apply, so what do I see from this? I see the following thing. I take this, and I know that ds equals 0, so 0 equals to ds to de of x multiplied, instead of de, I'm using f dx. F dx.
Down there is the x vector, right? Not
Sorry.
And the line that you just wrote is the x vector.
Hey.
not e.
דו S לדו E למטה
כן,
בהתחלה.
יש x וקטור, אבל למטה פה. לא, בצורה הזאת. כן. זה בקטנה.
Keep the x constant.
This guy? Okay.
No, on the
No,
derivative.
the x is
On the
supposed to be
derivative.
constant instead of the e.
X, okay. Sure, thanks. Alright. This, and we also have plus ds to dx e dx. Right? So we got the following. ds to dx of e equals minus ds to de of x f. Okay, so we started from one state, we reached another state. On the way we got this equation. Right. Somehow it's going to be related to temperature in a second, but you see I used reversible process, adiabatic process. I used a lot of processes on the way. So you can say, well, this is a very limited equation, right? Because you used all those processes. And then I say the following thing, which is kind of magic in thermodynamics. You say the following. Equilibrium state is independent of how you got there. The moment that you got to an equilibrium, you completely forgot where you came from. Okay? So this equation relates equilibrium states. So it absolutely doesn't care about what kind of processes I used in order to reach this equation. Okay? This guy connects equilibrium states. So I can forget about reversible processes, adiabatic processes, etc., etc., etc. I reach to this equation, I say, oh, if those are two equilibrium states that are connected by this equation, it will always hold. I'm forgetting about the reversible, adiabatic, say, this is very general. Irrespective of adiabatic or reversible process. This is kind of thinking, well, if you have an integral, okay, of a differential the integral over a differential, it doesn't care about what exactly the path that you had to make in order to get the result. The same thing happens over here. Because everything is related to the final, to the initial position, and the final position to your equilibrium state A and equilibrium state B, you don't care how exactly you got from one state to another. If you manage to get from one state to another, it will always hold. Okay? So this is a trick that physicists do. Mathematicians don't like it. But it is really, really fine. Right? I'm simply assuming I have those states and there exists a path. I use this path. The moment I use it, I can forget about it, throw it to the garbage, and just use this equation. Okay. Yes.
שתי שאלות. קודם כל, אתה מדבר פה על מצבים A ו-B, איפה אנחנו רואים אותם בעצם במשוואה? זו שאלה אחת, אני כאן אגיד השנייה. בעצם אנחנו כאילו צמצמנו ב-X, או שזה...
כן. Okay, so two questions. How do we know that where are those states A and B? So as I told you, this equation connects starting energy at one state to an energy to another state. And I'm saying those in first state and the second state are equilibrium states. Okay, this is equation written for equilibrium states. The same holds for entropy. This is part A. Part B is, yeah, kind of, if I have a multiplication by dx over here and I have a multiplication over dx over there, I can take dx out of the equation and I will say 0 equals to something multiplied by dx. Therefore, the something is 0. Okay. Great.
למרות ש-dx זה וקטור ולמכפלה.
Yeah, but because also the other stuff is going to be vectorial, right? So this is vectorial thing, and this is a scalar multiplied by a vector, so it's also a vectorial thing. Fine.
Okay. אז רגע, רק עוד פעם לא משהו, בחלק הראשון של השאלה בעצם, איפה במשוואה עצמה, שבסוף שאנחנו מגיעים אליה, אנחנו רואים את המעבר בין A ל-B?
We don't see it. We just say that since we started from equilibrium state and we ended equilibrium state by construction, we say that we start in equilibrium and we end in equilibrium. Therefore, this equation holds for any process that takes us from the initial state to the final state. Right? We say it. Okay? You don't see it from the equation. You have to assume it.
Okay, we see.
Okay. Great. So what do we know? We know that ds to dE equals, when x is constant, is greater than 0, right? So from this guy, we have dE to ds, x, greater than 0. Okay. So we can say dE to ds, it's our temperature. So it's not only that we have some function, we also have a connection between this entropy and the energy, and we call this derivative, which is, say that our temperature is always greater than 0, we call this derivative a temperature. Right? So this is the temperature that we wanted. It's all, again, defined by some constants that, or properties that appear in this equation. Now, when we plug this inside, what we obtain? We obtain that ds to dx of E equals to minus 1 over T F. Okay. So now I can write down, yes. From where to where? From this to this. Take dx out of this equation. Write it down. A dx plus this. This is the property of the second law, right? Remember? So the entropy is a monotonically growing function of the energy. I stated it. Remember? So you have to have axioms. And one of the first law of thermodynamics is an axiom. second law of the thermodynamics is axiom. Instead, there is an entropy. The entropy is monotonically growing function of the energy, and has this maximum property. You assume this. Okay? Okay, so now what we...
I don't get like how you got from this part to the second part.
From what part to what part?
On the...
From this guy?
Yeah.
To where? To this guy?
To this guy.
To this guy?
Yeah.
I just said it.
Okay.
So I had a lot of stuff. So remember there was a second law written over here?
Yeah.
Yeah. So in this second law I also stated that the entropy is monotonically growing function of entropy, of energy. What this guy means, that it's a positive derivative, so the entropy, if you take a derivative of the entropy with respect to the energy.
Yeah, and the second part.
So if this guy is greater than 0, these guys also have to be greater than 0?
Why?
Because, let's take, if you have ds to dE, let's do the following physical trick. It's 1 over ds over dE, right?
1 over d over ds.
Okay, yeah. Okay, we can do this trick. It's not exactly, I can justify it, okay? So if this guy is greater than 0, also this guy have to be greater than 0. Fine?
Whatever.
Why whatever? If you have a derivative of one quantity with respect to another, it's greater than 0, the other derivative is going also to be greater than 0. Okay. That's it. Whatever, I can prove it. If you don't like this trick, I exactly can reverse the derivatives, but this is the point of it. Is that dA to dB is 1 over dB to dA. Okay, so what we have, let's go back to our starting point of the entropy. ds, because this is very general, right? So ds equals to ds to dE to dE plus ds to dx dx. So instead of ds, what we can plug inside, so ds to dE, what it is, ds to dE is 1 over t. Okay, so ds equals 1 over t dE plus, what is ds to dx?
Minus 1 over t.
What? Minus what?
1 over
1
t
over
f.
t.
1 over t f
And
dx, right? Okay, so going one step forward, we obtain that dE equals to t ds plus f dot dx. Right? This is what we got, and this is the equation that we can use, and it relates energy to entropy and to work that was performed on the system. Moreover, it also tells us that the energy is a function of what? It's a function of entropy and the generalized coordinates. So it doesn't seem very informative right now, but we will see. So we have, or this is some sort of an extension of the first law of thermodynamics, right? So remember, there was heat over here. Now what we managed to do, we replaced heat by TdS. Okay, so there is basically a new knowledge from this term. It says, well, there is a relation in the amount of heat that you have inside your system to the energy, to the entropy that you also have inside your system. They are somehow related to each other. Heating up, the entropy is going up. Cooling down, the entropy is going down. Now, how we can use this variational principles. So what we have used so far is this guy, right, and some mathematical acrobatics with taking derivative of the entropy, playing with them, getting some specific equation over here that eventually led us to this equation. Okay? So the only thing that we have used so far is the existence of entropy and that this is a monotonically growing function of energy. We haven't used the maximal property at all. Okay? But the maximal property is the most important one. Why? So it's nice to have this equation. It's nice to have a relation to heat. It's nice to say, okay, so what are the variables that define energy? But this is a little bit nonsense because I don't really know what S is. So I don't want to play with S, but we'll see it later. But still, we haven't defined how to find equilibrium state. Right? I say, if I have equilibrium state and I'm going to another equilibrium state, something happens in between, and this is how they are related. But how I define equilibrium state? Okay? And to answer this question, I have only one tool so far, and this is the maximal property of entropy. I know that entropy has to be maximal at equilibrium. Okay? So basically it states the following thing. If I have a plot, this is energy, this is my coordinates, this is my entropy. Okay. I have, in some sense, 3 dimensions. Let's assume that I have x is not exactly a vector, but it's a scalar because I have some one-dimensional system. Okay. So I know that S is somehow growing. It's somehow growing as a function of E. Okay? So if I plot it, it's a 3-dimensional, 2-dimensional manifold that grows as a function of E. So let's assume that there is a curved surface that, as a function of entropy, the top of this surface describes the entropy of the system, and it grows as a function of the energy. The maximal principle states the following thing. If you cut this hypersurface at a constant energy, so if you plot here a 2-dimensional plane which cuts the energy at some specific point, okay, and it's just a flat surface as a coordinate of s and x, it's going to cut, as a function of x, it's going to cut this entropy, or this hypersurface of the entropy as a function of E and x, at very specific positions. So if you look where it actually, I need another color. So if we think about it, how it cuts this hypersurface, you're going to get a very specific function. So this green line is the positions where the hypersurface and the flat plane are intersecting each other. Okay? Are intersecting it. So you keep energy constant, and you look on where the hypersurface that describes the entropy cuts the flat surface that describes constant energy. You will see that there is one specific maximal point. Okay? So one specific maximal point. The second law of thermodynamics says to us, if you leave your system on its own, it will reach a position where the entropy is maximal. Okay? So what do you mean you keep your system on its own? You keep energy constant, so the system lives only in this two-dimensional plane, flat plane. The entropy have very different values for different values of x, which is your coordinates. What's going to happen is that eventually it will pick up one specific solution, one specific point where it's maximal. So this is the principle of finding properties of internal coordinates of the system by using the maximal principle of entropy. Okay? So if you want a simple idea in your head, let's assume that I have a system and I separate it, and inside the system I have different particles, red particles and blue particles. Okay. And I put a semi-permeable membrane over here. And this is my x. So let's assume that this preamble can move to the left or to the right. Okay? And I'm asking you, so the total energy of the system is kept constant. All right? The total energy of the system is kept constant. This guy can move to the left or to the right, and it's free to move. There are some specific amount of particles on the left-hand side, and there are some specific amount of particles on the right-hand side, where this membrane is going to stop. Okay? Where it's going to stop. So the idea of maximal value of the entropy says to us that, well, if you plot all the different properties or all the different values of entropies for all the different positions of x, the equilibrium state is where this entropy is going to be maximal. So this is the principle of the maximal value of the entropy. If you lose your system on your own, there's always some maximum value where it's going to be stuck, and this property is the it's the equilibrium state. Now in practice, if you do this experiment at your home, you will see that this membrane it's never stick to one specific position. Okay? So if you look on x as a function of time, you will see something that looks like this. There are always going to be some fluctuations because those particles, they are bombarding the membrane moves to the right, it bombarding it from the left, it moves to the left, etc., etc., etc. So the position is always going to move around. When we are talking about equilibrium energy or equilibrium value of x, it's the average value. So when we're saying something about the maximal entropy or the equilibrium state, it says that, well, this equilibrium or this average value is not going to be a function of time anymore. It's going to be constant, and this constant value, okay, it's related to the maximal value of the entropy. Okay? So this is the idea of how we define equilibrium state. Maximal principle of entropy. This is how we get from one equilibrium state to another equilibrium state. When we already forgot about the heat, and we're only using T and ds. Yes.
איך יכול להיות ש-DQ שווה ל-TDS, אבל DQ לא מסלול ו-TDS לא?
Great. If you go from one equilibrium state to another equilibrium state in a reversible process, you're going to get this one. Okay? Yes?
Did we demonstrate anything about the shape of that manifold, or it's just, you're just assuming that?
I assume, this is an assumption. This is some sort of an axiom. Okay? I know that the shape, and we'll get to this point a little bit later, but we know that it has to be at some specific shape that there is going to be one specific maximal point. Okay? Okay, so this is part of our assumptions about why entropy is maximal. We assume that it's maximal. We see everywhere around us that indeed equilibrium states are reached for maximal entropy. We use this extensively, but it's still some sort of an assumption. Right? Great. Now, the only problem with this principle, right? So energy is, well, you used to energy, temperature, nice temperature, but entropy it's not a nice quantity, right? It's not something that you do in your daily life. And this idea of maximal entropy, well, yes, it's nice, but it's cumbersome. So what kind of a DS you already had? You mentioned this. In analytical mechanics, you had minimal action or whatever, but it's somehow always been related to Lagrangian, which is something to do with energy. The same goes over here. So instead of having variational principle, so maximal entropy, I don't like entropy, but I like energy. So I want to have a variational principle not for entropy, but for the energy. Okay. So let's go from this principle of maximal entropy to another principle that relates to energy. So what do you think? If I have maximal entropy and at equilibrium, what's going to happen to energy at equilibrium? Lucky guess. Why? Okay, so let's see why. All right? Let's see why. So it's not really difficult, but maximal entropy states the following. We have ds to dx at E equals 0, right? And it's maximal, so we have d square s to dx squared, constant E, smaller than 0, negative. Right. So this is the property of a function. Let's assume that x is not a vector, because otherwise I will be stuck here forever to describing all this gradients, etc. But let's assume that x is one coordinate, like over here. Okay. And we know that at maximal point, the first derivative is 0, the second derivative is negative. We've all been taught this at our high school. Now, all this is applicable when the energy is kept constant. Now, what happens if I keep my entropy is constant? So I'm keeping my entropy constant, and I want to see what happens to the energy of the system at equilibrium. So S, E, and X equals to constant. So we know that ds to dE, well, keeping x constant, dE, plus ds to dx, keeping E, dx, equals to 0. Right? This is simply ds, and s is equal, so this is, let's write it down, this is ds, and since s is constant, ds is 0. Great. Okay, so out of this equation, we're getting the following. dE equals to minus ds to dx with constant energy divided to ds to dE at constant x multiplied by dx. So what we know from here, that dE to dx equals to minus ds to dx of E divided by ds to dE by x. Okay, so if we call this P dE to dx, this point P, what we have is, first of all, let's see, what is ds to dE?
1 over t.
1 over t, right? So we have minus t ds to dx at constant energy. But what is ds to dx at constant energy? Sorry?
What is p?
P is just, I'm assigning the first derivative of energy with respect to x as p.
Does it have a name?
Forget about it. Okay? Let's forget about it. Just look on the derivative of the energy with respect to x. Okay?
Constant S.
Sorry?
At constant S.
Exactly. Constant x. So here it's also constant s. Because ds here is 0. Because ds here is 0. Here is plus something multiplied by ds. But ds is 0, so there is nothing that is something. So all of this is the derivative of e with respect to x with a constant s.
That's why you change like from normal derivatives to
Yes,
other
exactly. Exactly. Because in general setting, see, energy is a function of s and x. So when I write down the differential is something multiplied by dx plus something multiplied by ds. But ds is 0. So we forget about this thing, and whatever stands at this part is the partial derivative of e with respect to x with constant s. Okay, so we reach this point, but what is ds to dx with constant e?
0.
0. So all of this is 0. So at equilibrium, we know the following. The derivative of e with respect to x, when we take constant entropy, it's maybe maximal or maybe minimal, right? This is a good sign. Now we have to go to the second derivative in order to find out whether it's maximal or minimal. So this is why I have written t over here, but we don't really need it. So let's find out what is the second derivative of this nasty guy. Okay. So what is d squared e to dx squared constant entropy? Actually we need it. I like the t. I like the t. I have t in my notes, so let's use it. Okay. It's just an assignment of what is d to dx. So this guy, it is dp to dx with constant s. It just looks nicer. Okay. So the next step is to say the following thing. How I can describe this derivative? I can describe this derivative as the derivative of p with respect to e with a constant x multiplied by de to dx with a constant s plus dp to dx, dx is a constant e, dx to dx. I'm taking the derivative of p. P is a function of e and s, right? So this is what's all getting e and x and s. So this is all what's getting out of this equation. Now I can continue. What is de to dx with a constant s? So this is p, right? So we have dp to de with a constant x multiplied by p. What else do we have? So dx to dx is simply 1. So this is plus dp to dx with a constant p. What is p? P is 0, right? Because the first derivative of the energy with respect to x at constant entropy is 0. So we left with dp to dx with constant e. Okay, so now it's d to dx of whatever p is. P is minus t ds dx e. Minus t ds dx e e. So where it leaves us at the following. So we have d to dx of minus minus ds to dx of e minus ds to dE of x. Okay, so I again I replaced this temperature with this expression of ds to dE and constant x. Okay, so this is the following. Minus d square s to dx squared divided by ds to dE of x plus ds to dx with constant e multiplied by something. But ds to dx with the constant e is 0 because we are working at equilibrium state. We don't care about it. This is equals 0. And we're almost done. So eventually we're getting to that d squared e to dx squared of s equals to this guy, it's 1 over t, so this is minus t multiplied by d squared s to dx squared of e. What is d squared s by dx squared? We don't know, but if we're at equilibrium,
It's negative.
exactly, it's smaller than 0. So what we got is d squared e to dx squared at equilibrium, it's positive, while dE to dx is equals 0. So E is minimal. Okay?
What
So-
is that?
Sorry?
The DE over
We
here?
proved it. We proved it.
Alright.
Okay, we proved it. So we first proved that the first derivative is 0, then we took the second derivative and we proved that
Oh,
it's...
yeah, okay.
Okay. So this is extremal point, and then we show that this point is maximal.
Yeah.
Minimal, sorry. Okay, so what we can say that at equilibrium, we don't have to talk about, oh, the entropy is going to be maximal. We can talk about energy. The energy is going to be minimal. And this sounds much more applicable, right? So if you're thinking about different systems, you usually don't think about systems in terms of energy, entropy. You usually say, okay, what's the entropy of the system? What's the energy of this particle? When I throw up this pen, what is the energy of this? I don't think, well, how entropy is actually changes as a function of time. No, it's always the energy. This is the, for us, usually, this is the natural thing to think about it. Now we have a principle to say what happens in equilibrium. For example, let's assume that I have a potential that describes a single particle.
Can I ask a question?
Sure.
Why are you ignoring the number of particles? It makes sense that S and also E is a function of the number of particles. I have 10 particles.
But it's the closed system. Closed system. I can do all of this, but it will take me much more time if I have different number of particles inside the system, many other coordinates, etc., etc. But still, it's a closed system.
Okay.
So the moment that I introduce my particles, I'm not getting particles in or getting particles out. Okay? So the idea of minimal energy is as follows. If I have, this is the energy of the system. Okay? And we already know this from first year classical mechanics. We can plot, and this is x. And we can plot this energy, potential energy or whatever. And let's assume that we have a plot that looks like this. Okay? So this is the energy of the system as a function of x. What is equilibrium? Equilibrium, so in classical mechanics, usually you put a particle over here and you look as this particle slides down and goes up and goes down, etc., etc., etc. Equilibrium means that you pick one single point, which is going to be over here, and you say, this is the equilibrium this equilibrium state of my system. So you have many different energies. The system can obtain different energetic levels. But eventually what you have to do is choose the minimal value of the energy as a function of your coordinates. You say, this is equilibrium. Now, it's not that the system sits exactly at one specific point and never moves out of it. It's like in classical mechanics, so this is, if this is a green ball, describes the system, it can move up and it can move down. Those motions are fluctuations. Equilibrium state says, well, its average value, or most probable value, is not going to be modified as a function of time. Okay, so again, if we're going back to our example of a membrane, or any other thing, so if you look on the energy as a function of time, it will start to fluctuate. It can go up, it can go down. But there is some specific value that it's not modified, and this is equilibrium. Okay. So what equilibrium really means is to pick out of many, many, many different states that the system can have, a single one, which have a minimal value for the energy. We say, this is my equilibrium state. Okay. Now, this is already a very strong principle. Okay. We have an equation that describes how energy is going to be modified as a function of entropy, whatever, or coordinates, or number of particles. And we know what kind of energy to pick in order to find equilibrium. Right. So those are already the ideas. We started with some general things about heat, work, etc., etc. Now we have an algorithm. Right? What is the algorithm? Plot for me the energy of the system. Find the minimal value of the energy of the system. This is going to be your equilibrium. You want to go from one equilibrium state to another equilibrium state? Okay, this is how different stuff is going to be modified. Nice program, right?
Can I ask a question?
Yes.
But there is also another minimum of energy in this state.
Great. So the system, you are absolutely right. When I haven't proved it. Okay. So this is a property of a local minimum, right? So this is local minimum. This is local minimum. This is local minimum. What actually the second law states is that the system is not going to be just occupying some local minimum, but it's going to occupy a global minimum. Right? I cannot explain it to you by some arithmetical tricks over here, because those equations are local. Okay? But what actually the second law says that eventually the system will reach the global minimum of your system. Okay? By the way, all the ideas behind AI is exactly this. So you can think about a learning algorithm like an evolving system that tries to find a minimal point of a huge, when the number of states is huge and the number of coordinates is just billions and gazillions of different variables. But eventually, learning algorithm of any AI, ChatGPT or whatever, it's how to find some specific global minimum of the system. The learning process is an equilibration process. Now, to continue your question, the system can be over here and can be over there. But after a while, it will always perform some specific jump and go to the global minimum of your system. Okay.
So every state has only one
equilibrium? No. So you define equilibrium by the minimal value. All those states called metastable. Metastable. Why metastable? Well, when we describe statistical mechanics, you will understand why. But the system can be over here. It will fluctuate around this point, and after a while, perform a jump to the global global minimum.
If you have two minimums,
which are exactly the same.
Yeah.
That's related to phase transitions and Ginzburg-Landau. Another 10 weeks from now. Okay.
Doesn't that mean that in order to switch equilibrium position, we need to change the entropy level to get a different.
So the moment that you modify your so this is for constant constant S. When you modify S, the profile of E is going to be something different.
Yes.
Yes. So you can operate on S. When you modify S, maybe this profile will be modified to something that looks like this. Okay? So your global minima is going to be modified from this position to that position.
Yeah. So how could we ever have a reversible process?
What do you mean? So if those modifications are really small. So in practice, nothing is reversible. Almost. But you can be very close to it. Okay? So look, when I won't do it, right? When I throw this cup, it will break. Okay? It's not reversible, and most of the processes are like that. But if I'll do this, okay, and I'll then do that, the process is reversible. Somehow. Okay? So this is the idea. You act very slowly, and you always let the system relax, and you don't do anything abrupt. But according to your question, is basically that you almost do not modify your potential. That's it. That's the story. Okay?
But when we put the cup on the flow, with such more לתת energy and
I have invested energy and I took out energy. So I took my system, brought it back, and moved it forward.
It's like
okay. So I shifted my energy, but I haven't done anything with the entropy. Okay.
אפשר שאלה?
כן.
בגרף אבל יש כאילו נקודות יותר נמוכות מהממוצע, אז למה הממוצע זה האקוויליבריום?
מה? לא. באיזה גרף? פה?
כן.
זה כי אני צייר גרוע. אבל כי זה פונקציה לא, הוא צודק. So the question is as follows. So if I have different oh, I'm sorry, this is not E. You're right. This is X. This is not E, this is X. Okay?
Okay.
All right? You're absolutely right. This is not E, this is X. Because otherwise there are some lower minimas of the energies, and how come that I have an average that is higher? Okay, so this is X. Sorry. Okay, so I'm going a little bit slow today. Let's try to see two additional principles that we can use with this maximal energy and minimal energy and etc. Okay, so I want to show to you examples of what happens to energy of different states. Okay, so we have a system with energy 1, T1, and entropy 1. And we have system of energy 2, temperature 2, and entropy 2. So if those systems are in equilibrium, okay. So I have two systems. They are already in equilibrium. This is the energy of a system called A. לא יודע, לא שלנו. Are in equilibrium. So A and B are in equilibrium. I know that the energy of A is E1, the B of E2, etc., etc., etc. So I want to understand or find out how T1 is related to T2. How T1 is related to T2. Now, if I introduce a little modification.
These are the same system, just different states?
No, those are two different systems. Let's think about this is one eraser, the other eraser. and they are in a contact such that the whole system, this A and B, is in equilibrium, and I want to understand something about the temperature of this eraser, how it's related to the temperature of this eraser. Okay, so this is the question. Now, I introduce a small change in the energy. So I take energy from system A and I bring it to system B, or I take some energy from system B and I put it inside system A. Okay? So, so perturbation to energies, while keeping total energy constant. Okay. Now I know because the system is in equilibrium state, no matter what I do, when I modify something internally, okay, when I do something internally, because in equilibrium the system was in with maximal entropy, so my perturbation caused a slight change in the total entropy of the system, right? So the entropy was maximal. No matter what I do internally, I kick the system a little bit out of the equilibrium, the entropy is going to get down. Okay?
This is ds total.
ds total. So total change of entropy. So the moment it happened, I also know something about the total change of the energy. So dE total energy equals to 0, because there are some energy that go from B to A or from A to B, but the total energy is kept constant. Okay, so I know that the entropy, the total entropy, is the entropy of system 1 plus the entropy of system 2. Why? Because the entropy is extensive function. So delta S.
Why do you know that?
I assume this.
You don't even know what entropy.
No. I, at the beginning of this lecture, invented a concept. Well, you heard about it, but I said there is a function, and it's growing as a function of energy, as energy is extensive and entropy is also extensive. Right? So I put something, I don't microscopically explain to you what it is, okay? And I have this and that property, and it's a part of axiom. Don't ask me about anything about it. Okay? So this is how it goes. Later on, we will relate the entropy to the number of states of the system, etc., etc., etc. But for now, it's just a function. And this is how it went for the whole 19th century in thermodynamics. It's a function with specific properties. That's it. It's related to heat. Okay, so delta S is something that you've done to system 1 plus something that happened to system 2. Okay. Now I haven't.
Like necessarily.
Why it happens? Because I have a maximal entropy principle. I have it. I proved it.
So
right?
why is it negative?
So if it was in a maximal state, I did something. I kicked my system a little bit out of the equilibrium. The entropy went down. If you have a function, if you have a function, I have a function, right? I have a function. It was sitting over here. Okay. I moved it a little bit over here, or moved it a little bit over there. The entropy went down.
It was in equilibrium. So
it was in equilibrium. Yeah. I started R in equilibrium. Okay. Now, what is this delta S1? So this is ds1 to dE1 delta E1 plus ds2 to dE2 x delta E2. Okay, now delta E equals to delta E1 plus delta E2. It equals 0, therefore delta E1 equals to minus delta E2. Moreover,
why don't we differentiate S by x?
By x? Yeah. Because I kept x constant.
Wait, but
You ask me how exactly I did it? It's a miracle.
It's a bug.
You have a wizard.
Well, you see, I'm saying the following. I define to you a game. Let's take two systems, and somehow magically they are in contact and they are in equilibrium, and somehow, give me an example of a system, I will show you how exactly to do it, but somehow I modified the energies, okay, I modified the entropies, okay, but I kept the internal x's constant, right? Can I do that?
Okay.
Theoretically I can.
Yeah.
Practically, well, it depends on what kind of system you have in mind. Now, the next step is already being obvious. So this is 1 over the temperature. This is 1 over the temperature. So we have that delta S equals to 1 over T1 delta E1 plus 1 over T2 delta E2. Okay, since delta E1 equals to minus delta E2, we have 1 over T1 minus 1 over T2 delta E1. Moreover, delta S is negative. So we have this is smaller than 0. Smaller or equal to 0. Now, I haven't anywhere said how much of the energy I moved from system 2 to system 1, or how much of the energy I moved from system 1 to system 2. So, delta E1 is unconstrained. What it means? It can be positive, it can be negative, it can be whatever I like. But this equation has to be always satisfied no matter what the value of delta E1 is. So when it's always satisfied, if I put here plus 2, minus 2, plus 0.3, minus 0.7, whatever. The only situation when it's going to be always satisfied is when 1 over T1 equals to 1 over T2. Right? When it's 0. So basically what I get, that in equilibrium, T1 equals to E2. Right? We know that we put two bodies in a contact. You wait, and after a while the temperatures of those two bodies are going to be exactly the same thing. Usually this is how second law of thermodynamics can be explained, described. You put two bodies in a contact, the temperature is going to be equal to each other. We haven't assumed anything about temperatures. We have actually defined temperature on the way today, but the maximal principle of entropy dictates this fact. Okay? You don't need to assume this from start. Okay? You can assume something about entropy and then get everything else out of those, or out of this assumption of maximal value of the entropy.
Why do you need the right side to be 0? I don't get it.
So, how this equation be satisfied? So I can plug here whatever number that I want. What number you want to put inside?
Positive or negative?
Positive or negative, but it still have to be this equation have to be satisfied. If delta E1 is positive, delta is 1 negative. Then it's going to be true. There's a statement. This equation is always true, no matter what the value of delta E1 is. You get out of it, it's only correct if this guy is 0. Right? Can you have any other solution?
Well, the solution can change depending on the...
No, the temperatures are constant.
Fine.
Right? The temperatures are constant. Because remember, what happens in equilibrium, the different generalized forces are constant. Right? Yeah. So the temperature is not the function of time, it's not a function of anything. You put this, the temperature is exactly the same as it is, because nothing is going to change as a function of time. Okay? So T1 is constant, T2 is constant. This can get whatever value that you have. This means that 1 over T1 equals to 1 over T2. Now, moreover, I can do the same trick. I don't really have a lot of time. But I can do the same trick, and I ask the following question. Okay? Let's assume that I had two boxes, one with T1 and T1 and S1, and then another one with T2, T2 and S2. And they were not in equilibrium. When they're not in equilibrium, T1 can be whatever I like, S1 can be whatever I like, E1 can be whatever I like, and I put them in a contact. Right? So not in equilibrium. And I put those two guys in a contact. Right? I build a connection between those two guys, and the heat can flow from one box to another. That's again A, and this is B. So what will happen then? If I will do the same tricks, okay, basically I will assume that there is a maximal entropy and that nothing is going to happen, and the total system is in equilibrium, basically no heat getting out of the A plus B system. What I will get is that the heat is going to flow from the system with higher energy to the system with the lower energy, right? This is an assumption of the second law usually, and that the temperature that is going to be, that was higher, going to get lower, and the temperature that was lower is going to get higher, right? Again, I don't need to assume this. The maximal entropy principle will dictate this behavior. Is as in equilibrium, the temperatures are exactly the same. Okay? If you have two systems out of equilibrium, when you put them together, there is a flow of heat from one place to another, and the heat will flow from higher energy to the lower energy, and the higher temperature is going to get down, and the lower temperature is going to get up, because eventually they have to meet somewhere according to this principle over here. Okay, so we are done for this week. What we still haven't covered, this is because of me, I was too slow today. What we still haven't covered is Legendre transformations and potentials of energies and etc., etc., etc. We will cover this next week. I don't think that you need this for your homework, but if you do, let me check it so you don't have to work on it this week. That's it. See you next week. Thank you.
אם אני נגיד, אם אני רוצה אז זה צריך להיות שלילי
או אפס, זה קטן שווה מאפס. נכון. שלילי או אפס. יפה. אבל זה לא יכול לשנות אותה. עכשיו אתה מניח שזה שלילי, אז זה חייב להיות חיובי או אפס.